Hello everyone and welcome to the last topic of this course. It is angular momentum, the final bit of equivalence in between the linear and angular motions. We had position and velocity and acceleration and energy and forces and torques, mass and moment of inertia. Finally, there's momentum. Linear momentum was used in collisions, mainly. Angular momentum is a bit more universal, a bit more versatile. Much like linear momentum, and here you'll hear me say momentum a lot, so please be patient. Much like linear momentum, angular momentum is a quantity that is conserved, not just in a collision, but over time. In a nutshell, it's why all of the planets of the solar system rotate in the same direction with respect to the sun. It is the reason why most of the planets rotate around their axis in the same direction. Some are retrograde or rotate at weird angles. I think Uranus is the one that's tilted almost at a 90-degree angle, but those are exceptions due to cosmic events that I don't remember. Angular momentum is conserved, again, if there are no external torques acting on the system. Much like the torque is defined by where a force is applied on an object using a position vector r, angular momentum is defined as where the object is with respect to an axis of rotation and what is its linear momentum with respect to that object. You can think of it as either what is the quantity of rotation of the object or what is the apparent quantity of rotation. Let's take the highway, for example. We decide to do a physics thought experiment and we go sit by the highway and we look at cars flying by. What we'll do is this. We'll see the cars flying and rolling and driving. We see the cars come from our left, for example, to our right. We do a rotation with our head. The car appears to do some kind of rotation around us. The only reason we know it doesn't is because our eyes can focus and see that the distance is not constant. It shrinks, reaches a minimum, and then expands again. But we can find an angular momentum, nevertheless, for such a particle. Just consider a particle at the moment. The angular momentum is labeled with the letter L. It is a vector. It is capital L, be careful, and it is the cross product in between the position vector and the momentum vector of the object. As with all of our cases, we're assuming the mass of the object is constant. We can extract it from the momentum and factor it out of this thing. You can write the angular momentum either as r cross p or m times r cross v. This is the angular momentum. It's a cross product, so it is two vectors multiplied together, giving us a third vector. The magnitude we can find simply by taking r times p times the sine of the angle between the two vectors, or mrv times the sine of the angle between r and v. A short schematic could look like this. And here at 0, 0 is where we look, or the point with respect to which the angular momentum is calculated. The angular momentum only has meaning when it is specified with respect to a point. Usually we take that to be the origin to simplify the math. The direction of L is also always perpendicular to the plane formed by R and P. The cross product of the two vectors give you a vector that goes out of the board or into the board in this case. In a nutshell, that's the angular momentum. For a rigid body, like we had when we found in part 9 the moments of inertia, and what we consider for static equilibrium, what we used for torques earlier, a rigid body is just a collection of individual point particles. What I had written here before was the angular momentum of a point particle. A rigid body is just very many of those point particles. To find what the total angular momentum of a rigid body is, for example, of this marker, you consider the sum of all of the angular momentums of all of the individual point particles. I'll spare you the algebra, partly because I don't remember it, but the important bit is this, is that so if all forces are on the xy plane, then the angular momentum, by definition, will always be on the z-axis, that way or this way. That component, which we call Lz for a rigid body, is then given to you by this. It is the moment of inertia times the angular velocity of the body. Note that the rigid body can be a point particle, and we have the moment of inertia for a point particle when it rotates about an axis that's far away from it. You can do the analogy write the analogy with the linear momentum, where for the linear momentum we have, in both of those equations, we have the momentum, angular or linear, that's equal to the product in between the inertial property, moment of inertia or mass, in angular or linear motion, times the speed of the object. Velocity really, but we're considering only one dimension, either along the z direction or here x or y. So that is it really. For a rigid body, this is just what you need. And you will then be able to link this to the moment of inertia that we had before and the angular velocity and speeds that we had again before in part 9. Remember what Newton's second law for linear motion was, how it was really written, how it was originally stated. It was stated to be the net force is directly proportional to the rate of change of linear momentum in the same direction. So really, it was this. And all that we did was take the derivative with respect to time of the previous equation, p is equal to mv, and the mass is constant, so the derivative with respect to time of the momentum is m times the acceleration, which is the sum of the forces. If we do something similar with the angular momentum, this is what we get. We get dlz dt is equal to I d omega dt. The moment of inertia, much like the mass, is constant, so when we derive a constant, it gives us 1. You can do the bits. It gives you I d omega dt, and d omega dt is the instantaneous angular acceleration, alpha. And that, we had seen in the previous video, is Newton's second law in rotation. It is the sum of the torques. So we can write the sum of the torque is dl dt. And that is Newton's second law in angular form, the final version. Now, I mentioned something earlier at the beginning when I presented the concept of angular momentum. I said that it was conserved. That it was conserved if there are no external torques acting on the system. That stems from Newton's second law. If the net torque is 0, that means that dl dt, the change in angular momentum over time, is 0. Now yes, I agree, linear momentum symbol is a p and the symbol of angular momentum is an L, but the word linear starts with an L. Don't read too much into it. You need to accept it like everybody. It's a convention. Going back to this, if this net torque is 0, that means dl dt is 0. We have conservation of angular momentum. And this is very, very powerful. Much like the conservation of linear momentum allowed us to look at collisions while ignoring whatever was happening during the collision. Here, we can explore different states of rotation for an object while ignoring what happens during the situation. We can just look at two different states before and after some conditions. And this is the conservation of angular momentum. You can also rewrite it as the final net angular momentum is equal to the initial net angular momentum. Some bits of takeaway. The three laws of conservation we saw, conservation of energy, conservation of angular momentum, and conservation of linear momentum, those three laws hold beyond what we've done in this course. They hold for most, if not everything that happens in the universe, unless extreme cases that I don't know because I don't remember them and I haven't studied them. Also, that you don't need to worry about unless you go in do high-level research and studies in physics. Then you might need to consider it. But it still remains true when you consider special and general relativity, again, unless extreme cases. And it remains true also in quantum mechanics, the study of quantum physics of subatomic particles. Angular momentum is actually a key part in quantum mechanics, and the conservation of angular momentum. They are the very foundation, and many things that we found, that we studied, can be derived with these three laws: conservation of energy, conservation of linear momentum, conservation of angular momentum. I would need to go and look at notes and books to refresh my memory on all of this, but I believe it could be done. And if not, feel free to correct me and let's talk about it. I'm always willing to talk about physics. And that's it. This was the final topic, conservation of angular momentum. If there are any problems you wish me to solve, or if I see many people asking for questions about the same problem, I'll do something. Thanks very much for watching all of these. I hope they were useful. Thanks very much for your presence this semester. I look forward to seeing you again in the physical world of the college next semester. Good luck for everything that you need to do in this final month of the semester. Good luck for your final evaluations, whatever they are, however shape they take. Good luck this summer. Take care of yourselves, both mentally and physically, and I'll see you in the next term.